Hello everyone, and in this video we are going to talk about second order linear equation. Okay, second order linear equation, and we are basically starting out with a constant coefficient equation. Okay, equation with constant coefficients, okay, and for all for the starting part we are going to only talk about homogeneous equation, and then I will going to show you how to work out the inhomogeneous equation. So first of all, we know that, let's say, a equation. Okay, so what's the general form? The general form will look like this. No, general form will look like this. Form will look like y double prime plus a y prime plus by equals to 0, right? That's the general form, and a and b are some constants, and this is a general form of homogeneous second order linear equation with constant coefficients. Clear? Now we want to know how to solve this problem, right? And why I am specifically doing this thing, I'm quite sure you guys already know what to do here, but again, this is a revision, and I'm doing this because I want it to be precise and exactly what is happening, because we are going to use this idea in a later part. Okay, so you see, since in this case we do not know how to solve this problem, okay, explicitly, without directly directly attacking this problem. So what we do is this OD, we want to use something which we know. So we will convert this OD to a algebraic equation. Okay, algebraic equation. So what we are trying to do here is this. See, let's say that if one assumes that there is a function, y of x, let's say, which is e power r of x, and that satisfies, let's call it star, satisfies star. Okay, satisfies star. So here we have to find r such that this happens. Okay, so what is the guarantee that something like this will happen? Okay, so that's the question. So basically, if we can find some r such that e power r x will satisfy this equation, then we are basically done. Okay, and if something like this happens, then you see y prime of x is nothing but r e power r x, and y double prime of x will be r square e power rx. Now if you put everything together, the equation, if one puts the above values in star, okay, what do we get? We get r square plus ar plus b, okay, times e power rx. This is nothing but 0, right? That's what we are going to get. And what does that imply? That will imply r square plus ar plus b equals to 0. Why? Because e power rx is never going to be 0 for any x in r, right? For any x in r. Okay, so that is fine there. So this equation, the equation which we derive like this, if we remember, it is called a characteristic equation. I hope this is the spelling is correct. Characteristics. Okay, there is a mistake here. Let me just put it this way. Characteristic equation. Okay. Okay. Well, now if we solve the characteristic equation, you do realize that we are going to get two roots, right? It may be same, maybe equal, or maybe distinct, maybe complex, but we are going to get two roots because this is quadratic equation. And once we get two roots, we can just put it in the function and we can get solutions out of it. Okay, so first case 1, distinct real roots. So what I meant by this is, you see, there are roots r is nothing but r1, which is not equals to r2. Okay, so in this case, what are the solutions? Therefore, the solutions which you are getting, the first solution which you are getting, y1 of x, let's call that, you can write it as e power r1 of x, and y2 of x. Another solution you are also going to get, you are going to get it as e power r2 of x. Okay, right. So those are the two solutions which you will get out of this. Now you see what is happening is this is a linear equation, right? So check that if y1 and y2 solve star, okay, see this y1 and y2 is of this form, but basically this holds for any two solutions. So basically if you have any two solution y1 and y2, so you do realize that alpha times y1 then alpha times y1 plus beta times y2, so this is independent of this case, solve star for any alpha beta in R. Okay, so this always holds. Okay, and why this holds? Because this is linear, because of linearity. Okay, so you need to check this part. Please check this. So this is one of the characteristics of linear equations. So once that is true, you see here what we have is y1 is a solution, y2 is a solution. So therefore y of x, we will call this a general solution. So we will write it as G. Okay, this given by y e power r1 of x. So alpha e power r1 of x plus beta e power r2 of x. Okay, this solve star. So basically this is the general solution. Let us write it like this, is the general solution. What do I mean by general solution? I mean that all possible solutions of this equation has to look like this. There is no other way. Okay, for any alpha beta in R. Okay, now a big question, and this is very, very important. How do you know? How does one know that any solution of star for the, let's say, at least for this case, let's say real distinct case must look like this, must look like yg. Okay, so what is the guarantee here? You do understand what I'm trying to say. See, general solution is nothing but all possible solutions. Okay, see, this equation is a linear equation. Y equals to 0 is of course a solution. You do realize that, right? You see, y equals to 0. So yx identically equals to 0 is always a solution. Okay. Now, basically, we are trying to find the other non-trivial solutions, and what I am trying to say is this: all possible solutions are contained in this family. Okay, so what is the family? If you are varying alpha beta, so let's say alpha equals to 0, you have beta times e power r2x. Alpha equals to 1 and beta equals to 0, you get e power r1 of x. You do realize all possible combinations are the linear combinations. So basically it says that all possible solutions will look like this. Okay, so what is the guarantee? These questions will be answered in another few lectures. Okay, when we are going to talk about systems, I will do it for a system, and then that will actually imply in this case also the exact same thing. Okay, so that is there. So basically what I am trying to say is this: if you have a, so please remember this, if you have a second order equation, at least constant coefficient equation, it is also holds for variable coefficient, doesn't matter, but for now, since I am doing constant coefficient, let's just assume that constant coefficient equation, if you have you always will have two such functions such that the linear combinations will actually give you all possible solutions. Okay, right? And what do I mean by two functions? They are very special functions which we will later call it as a linearly independent function. Since I did not do it right now, we'll do it later in another few classes, and then it will become much clearer. Okay, let's look at the second case. So second case, okay, case 2. What is the second case? Case 2 is the real and equal okay, so basically what it means is we are looking for R, which is R1 equals to R2. Okay, and in this case, of course, you have one solution y1 of x given by e power R1 of x. Okay, but you can't get another solution y2 of x because it will be basically same as y1 of x. Okay, so in this case what we do is this is a solution of star, right? Huh? How do you get another solution? So this is a trick which actually you can use it, and this is will be a part of assignment. So what you can show is this: to find another solution, what we do is this: to find another solution, okay, let y of x, we will define a new function y of x is nothing but u of x e power r of x. R is r1 or r2, whatever you want to call it, basically that. Huh? Now you see, if this is a new function and this u is a smooth function, so is a C infinity function, we will assume that. So essentially what I am trying to say is this: we are trying to find a C infinity function, an infinity differentiable function, that is C infinity is infinity differentiable function, such that yx given by ux times e power rx will also satisfy star. Okay, and what is r? R is r1 or r2, whatever you want to call it. So if that is the case, then y1, y prime and y double prime you can actually calculate, and then that will satisfy the equation. So let's just put it together. If we put it together, it becomes e power rx u double prime plus 2r u prime plus r square u plus a e power r x u prime plus r u plus b u e power r x equals to 0. Okay, so just by substituting the value of y prime and y double prime in the equation, okay, we get this. It's a very straightforward thing, nothing special is happening here. Okay, so if you see now, the thing is this: you can rewrite this thing and it will look like this: u double prime plus 2r plus a u prime. See, e power rx is basically non-empty, non-zero, right? So we can just throw it out, plus r square plus ar plus b times u equals to 0. Clear? So now you see, r is a root of the characteristic equation, and the characteristic equation is given by r square plus ar plus b. So if r is a root, then r square plus ar plus b is equals to 0. So basically this term is gone, this is 0. Okay, so that will imply that your equation looks like this: u double prime plus 2r plus a u prime is 0. Clear? Now this is the first order equation. See, r is a repeated root. Okay, r is a repeated root. So basically that will actually imply that 2r plus a is equals to 0. Clear? And if this is the case, then that will imply that u double prime is equals to 0, and I am just looking for one u which will satisfy this. So ux given by c1 plus c2 of x will satisfy such an equation: u double prime equals to 0. Yeah. Okay. So therefore y2 of x, we can define it to be c1 plus c2 of x e power r x. Okay, so then, and what is c1 and c2? C1 and c2 is in r, where c1 and c2 is in r. Okay, now you see, what is the general solution in this case? General solution, so yg is nothing but alpha times y1 plus beta times y2, as I told you, right? Okay, so it is alpha times e power rx plus beta times c1 plus c2 x times e power rx. So essentially this will look like, let's say, alpha 1 plus beta times x, okay, beta 1 times x, or I mean some constant. So basically what I am trying to say is this: it is alpha plus beta times c2, let's just call it beta 1, okay, times x e power rx. So that is the general solution. Okay, that, so therefore the general solution, so where alpha and beta 1 is in R. Okay. So, what is the general solution when both roots are same and real? It is alpha plus some constant plus another constant times x e power rx. Okay. Right. Now, let us look at the third case, case 3. Case 3. So, what is the case 3? It is the complex conjugate root. Complex conjugate root. Okay. So, what I mean by this? I mean that R, so you will have two roots. So, if R1 equals to U plus IV plus minus IV, okay, R1, 2. So, basically 1 is plus and let us say 2 is minus. Let me put it this way. Okay. So, if R1 is U plus IV and R2 is U minus IV. Clear? Okay. So, in this case, what is happening is this. See, you are going to get two solutions here. So, you see y1 of x in this case will look like e power r1 of x, right? So, e power ux times e power I vx, which is cosine vx plus I sine vx. Okay. And y2 of x will be the exact same thing with the minus sign here. So, it is e power ux cosine vx minus I sine vx. Okay, right. Now, we have to understand this, that you see these y1 and y2 I can write down as a linear combination of this is let us say general solution. But the problem is this, note that here that y1 or y2 does not matter, or y2 are both complex, right? And the thing is, we are not looking for any complex solutions, we are looking for a real solution. So, how are we going to get a real solution? Tell me. So, what we are going to do is this. See, we are going to write down a small theorem here. It's a small theorem. So, let us say if, let us say y1 plus iy2 solves, or let us call it z1 plus iz2, that so let us z1 plus iz2 solves star, clear, then both z1 and z2 solves star. Okay. So, z1 and z2 are real, but the thing is, let us say z, which is given by z1 equals to z2 plus iz2, that starts solves the equation. Then individually z1 and z2, those are all real, right, real functions, they solve star. So, how do you prove it? Very easy. So, please check this part. The solution I am not going to do it. Please check. Substitute z prime and z double prime in star, and then what do? You equate the real and equal parts. Equate real and equal parts. Okay. So, you get the theorem. So, I am going to use this theorem here. So, what I am going to do is this. What I have said is this is z, which is z1 plus iz2 if it solves the equation. So, here you see, if you see properly, it is e power ux cosine vx plus I times e power ux sine vx, and similarly here also the same sort of thing happens, y2 with a minus sign. Okay. So, here you see, since z equals to z1 plus iz2, so here z1 is this, z2 is this, both of them solve the equation. So, individually z1 and z2 solve the equation, though, right, and then they are real, right. So, therefore the general solution yg of x can be defined as alpha times y1 of x, which is e power ux cosine vx plus beta times e power ux sine vx. Clear? So, if you want to write it properly, you are basically end up with alpha times cosine vx plus beta times sine vx times e power ux, right. and here alpha beta is in R. I hope this is clear to you. And we are going to use the same sort of concept later also. Okay, so I want you to understand what is happening here. Right, now we move on to a very similar situation for a different equation. So we move on to something called a Cauchy-Euler equation. Cauchy-Euler equation, right? So what is Cauchy-Euler equation? Let's just write it down. You see, essentially we are looking for a equation which looks like this. Any equation of the form x square y double prime plus a x y prime plus b y equals to 0, right? And here I am assuming x is positive. Clear? Then, so basically this sort of equation we call it a Cauchy-Euler equation. You see, one beautiful thing about this equation is the x square, the power of x which is involved with y double prime is 2, with y prime is 1, and with y is 0. Okay, so that is this beautiful structure, and this sort of equation is called Cauchy-Euler equation. Why are we trying to study this equation? Because we can actually, this is, you see, if you think about it, it is not a constant coefficient equation, but in some sense it is actually a constant coefficient equation. In the, and what sense? See, this is very well coefficients, but the thing is you can use the same sort of technique which we used in the first part to actually derive a solution. How can we do this? See, let's assume yx to be x power m. Okay, solves 1, let's call it 1. Okay, so if it does, then you see y prime, y double prime, you can calculate and put it here. Once you put it, what will happen is this: you are going to get x square m minus 1, okay, x power m minus 2 plus ax m x power m minus 1 plus b x power m, this is equals to 0. This is what we are going to get, and that will actually imply that m minus 1 plus am plus b is equals to 0. This is what we are going to get, because x power m, x is assumed to be positive, it's never going to be 0, right? Okay, now again you see 2, and again you see this is nothing but a quadratic equation which will actually again have 2 roots. So exact same sort of thing will going to happen what we did here. Okay, exact same sort of thing. So what I want to do is, please check this, check the theorem stated below. Okay, this is your work here below, and I will state the theorem. What happens is this: see a, okay, so the solutions. So basically, if m equals to m1, which is not equals to m2, okay, so if there are 2 roots m1 and m2 such that this happens, that m1 not equals to m2, okay, if this happens, then the general solution, as you can see, y of x should look like c1 times y power, sorry, x power m1 plus c2 times x power m2. Clear? So you have to do this part. Now if m1 equals to m2, real and equal, then how does it looks like? Yx will look like c1 times x power m. This will be the first, of course you are going to get that, m1, plus about the second one, what you are going to do is, you are going to get, see, in the earlier case we got just a x, here we are going to get log x power m. Clear? And see if they are complex, so complex conjugates. So basically m is u plus iv plus minus iv, then y of x will look like this: c1 times x power u cosine u v log x plus c2 x power u Okay, so in the both cases x power u is there, sine v u plus I v, that v log x. Clear? Okay, so you have to check this part. How do you do it? Exactly the same sort of thing what we do it in the last part. That same sort of idea will work in this case. So you please do this part, and with this we are going to more or less close our the study of equations, at least second order linear equations. So before we finish this the video, let's put down a question here. Question: check if this procedure, okay, not only this, the whole video, whatever we did, works for higher order equation or not. Higher order equations or not. Okay, so essentially you see it should work, right? Because you see what you are doing is you are basically reducing a ODE to essentially an algebraic equation. It can be quadratic, it can be third order equation, fourth order equation, right? So, but algebraic equation, if you can solve that equation, you actually have all the possible ways of finding the solutions. Okay, right? So please do that. So start with a, let's say, third order equation, and then try to do exact same thing. So basically with a constant coefficient or like a Cauchy-Euler equation, you can do that. So with this we are going to end this video.